2 that I gave for fall 13, you will have seen a similar question. No big deal. And I had brought in a fairly large supply here of information sheets because a couple of folks told me they wanted a new copy, and I see they've evaporated. How many else still want an information sheet? I'll bring some more next time. Or if you wish, well, yeah, tomorrow following your quiz, you can probably take the information sheet with you if you need it, because we have an abundance. Because as you know, for each quiz exam, we supply you with a copy of such. We proceed with topics regarding equilibrium involving salts of limited solubility in water. Salt effect, which we mentioned in brief at the end of our last conversation. A Coulombic effect, an electric effect, not a chemical effect. Silver chloride. Neither ion. Silver ion, chloride ion. Exhibits any Bronsted-Lowry acid-base properties of consequence in water solution. Therefore, solubility for silver chloride is correctly calculated, at least reasonably so, from its solubility product constant. Now, there are other aspects of solubility which at this stage of the game I'm not going to bother to talk about. Complex equilibria involving silver chloride, where in fact studies show that given the distinctly molecular character of silver chloride, we'll talk about the reasons for that later on. There's actually some AgClAq in this stuff because it has a distinct molecular character. There will be some AgCl sub 2 minus a dichloro complex of silver ion. All of these things are part of the solubility equilibrium established, or solubility equilibria established, when silver chloride is dissolved in water. But the main stuff by far is a saturated solution composed of, or containing, I should say, silver ion AQ and chloride ion AQ. So our solubility calculation is good enough for us at this stage of the game. Yet, if one takes silver chloride or similar materials and goes to the laboratory and prepares a saturated solution of this semi-soluble salt, in this case silver chloride, in a solution like 1 molar or 10th molar sodium nitrate solution, a solution in which neither principal ion reacts with silver ion or chloride ion, so there can't be any chemical effect on silver chloride in equilibrium with silver ion and chloride ion. What do we observe? We observe the silver chloride is a good deal more soluble in this sodium nitrate solution. What the heck is going on? I remind you again, this is a Coulombic effect, an electric effect. In 1 molar sodium nitrate solution, the sodium ion concentration is enormous compared to the silver ion concentration. The nitrate ion concentration is enormous compared to the chloride ion concentration. Do sodium ions have a natural affinity for chloride ions? Indeed they do. Why? Come on, Coulomb. They're oppositely charged electric particles. Do they not have a natural tendency from an electric nature standpoint to stick to each other? The nitrate ions have a natural affinity for silver ion. Damn right. Same reason. So, what happens? Because in order for silver ion and chloride ion to form silver chloride, the silver ion and chloride ion have to meet with each other, collide. You talked about stuff like this when you talked about kinetics at the end of 2045. In order for particles to react, they have to contact each other. Well, why is it that the ability of silver ion and chloride ion to contact each other has been significantly reduced when we have the silver chloride saturated in sodium nitrate solution? Well, consider the electric experience felt by a silver ion in the solution. Nitrate ions naturally swim toward it. But the nitrate ions can't swim by themselves because they are also dragging with them sodium ions. So what happens to an individual silver ion in this saturated silver chloride solution and sodium nitrate solution? A bunch of nitrate ions as well as sodium ions wrap around the silver ion. Just like a bunch of sodium ions are naturally attracted to chloride ion, but they don't swim by themselves. The chloride ions follow after them. The nitrate ions follow after them. So a bunch of sodium ions and nitrate ions also wrap around the chloride ion. So in essence, you have now insulated silver ions and chloride ions from each other. Made them more difficult to react with each other. The upshot of which is you can get more silver chloride to dissolve. And that is the salt effect. Enough said at this stage of the game. I can explain it in greater detail with activity considerations. We could even do calculations to show you how we can get the value for the solubility of silver chloride in sodium nitrate solution. But I don't see any need to go into that at this stage of the game. Why not? Because we don't have the wherewithal to go to our laboratory and measure activities. So we'll leave that consideration for another day. But I will tell you, if you go to a good analytical chemistry class, they will talk to you about activities. You remember what activity is? Did you hear about activity in 2045? You did? If you heard about colligative phenomena, the Van Hoff I factor, then you heard about activities. Activity, in essence, is a measure of the ability of an ion in solution to behave as an independent particle. Remember that colligative phenomena depend upon number of particles in the solution rather than what they are? What? So in this case, what we're doing is giving silver ion and chloride ion to act as particles independent of each other. That relates to this increase in solubility. But again, I'm not going to go further with the activity consideration than that. Let's go to topic D, which is back to chemistry. In parallel to what you folks have done in 46 laboratory, assignment 3. Where? Regarding calcium ion. Remember what you did in assignment 3? Anybody still in assignment 3? How many have finished with assignment 3? All right. You did 3 chemical tests. 3 different chemical tests to find out about detection of calcium ion in water solution by a methodology that's commonly called precipitation. The first test you did, assignment 3, 46L, was to see how calcium ion by investigation, see how calcium ion by experiment and investigation, see how calcium ion reacts with hydroxide ion. And observe the tendency of calcium ion to react with hydroxide ion to form calcium hydroxide. Not a particularly soluble salt of calcium ion. Then you gave calcium ion the opportunity to react with carbonate ion. Upshot, make calcium carbonate. Main ingredient in teacher's favorite weapon. And then at last you gave calcium ion the opportunity to react with sulfate ion. Upshot, make gypsum. You familiar with gypsum? Calcium sulfate dihydrate. Main ingredient in drywall. Do you know what drywall is? You ever had any experience at home? Home construction? Patching holes in the wall? Gypsum board, drywall, plasterboard, all these names apply to. This common building material for inside walls in the home. It's calcium sulfate, dihydrate, gypsum. That's a geologist's name for that, calcium sulfate dihydrate. Is that particularly soluble in water? Would you like to make walls at home that are particularly soluble in water? You as a little kid, you go along and you smudge the wall. Mommy comes along, give you a whack. Then gets out the sponge. Ha! But in this home, the walls were made out of sodium chloride. Oh! Look at this hole I created. The wall dissolved. Damn it. Also, you see these waters as part of the composition of this stuff? Under normal laboratory conditions, what is the principal phase shown by water? What is the principal phase shown by water under normal lab conditions? Liquid. Liquid. Do we also observe water in the vapor phase under normal lab conditions? Is there any water in this air atmosphere? If I take my cup, well, unfortunately you can't see through the walls of the cup, but I got some water in there. It's about half full. Now it's not quite half full. And I make a mark of the meniscus level. And I leave my open cup stand here till our next conversation. Will the meniscus level of the water be the same as it is right now? What will happen? Evaporation. Which means that in this stuff we call air, there are certainly water molecules in the vapor phase. However, under normal laboratory conditions, can pure water exist in the solid state or phase? Tell me, in 2045, did you study phase diagrams? Did you study phase diagram for water? I venture to say if you studied any phase diagram, you certainly studied a phase diagram for water. From a thermodynamic standpoint, you know what kind of diagram a phase diagram is? This is another illustration of the stupidity of these damn lousy general chemistry textbooks. You can tell how happy I am with these writings. A phase diagram is a free energy diagram. How much time did you spend in 2045 talking about free energy? Because although you did talk about enthalpy and changes in enthalpy, and did a bunch of Q calculations, how many entropy calculations did you do? How much studies of entropy did you make? This is a travesty. Because what you want to know about a chemical process from a thermodynamic standpoint is whether or not it can proceed under the conditions at which it is being studied, and you can't answer that with just delta H. So what the hell's the point of just doing delta H? I don't get these textbook authors. Their command of fundamental chemistry is zilch. They don't know what the hell they're doing, and I mean it. They don't bother to talk to you about free energy. For example, in the Silberberg text, till something like chapter 20. And so much of what they've already done is all based on free energy considerations, like phase diagrams. It doesn't make any sense. In any case, if you recall the phase diagram for water liquid, which we'll be studying again, because I know damn well in 2045 you didn't learn about that diagram as I need you to learn about it. So when you get to chapter 20 or 21, which is coming soon, we'll be talking again about the phase diagram for water. You'll see that under normal lab conditions, water cannot by itself exist in the solid state. It's impossible. But water's part of the composition of that stuff. Do you see at home your walls, which are gypsum walls most likely? Do you see your walls crying? The teardrops are running down because the water's running out of the gypsum. Have you seen that happen? Chemistry's marvelous. Because by interacting with calcium ions and sulfate ions in the gypsum lattice, water molecules are part and parcel of the solid state. How about that? Chemistry's neat. In any case, back to precipitation. And you're working assignment 3, 46L. You have a solution before you. You're doing an unknown analysis. You have found out that this solution is rich in sodium ion because flame test shows a long-lasting yellow to yellow-orange flame color. Whereas the flame color for calcium ion is commonly called fire brick red. Call it red-orange. That's good enough. And for those of you who have done assignment 3, which is probably, this is first stuff you do in assignment 3, you probably all know this, you can't find calcium ion by flame analysis if the system being tested is rich in sodium ion, because the sodium ion flame is too intense. It masks all the flame colors of all other ions which show a flame color. So you're forced, for such a system that's rich in sodium ion, to rely on chemical testing for calcium ion. And the methods which will be made available to you are 3 possible precipitation investigations. To give calcium ion the opportunity to react with sulfate ion to make gypsum, or hydroxide ion and make calcium hydroxide, or carbonate ion and make calcium carbonate. You've got this solution. Got sodium ion in it. You need to test it for calcium ion. You're doing an assignment 3 analysis. Which reagent will you grab? 10th molar sodium sulfate solution, 10th molar sodium hydroxide solution, 10th molar sodium carbonate solution. Which of these 3 reagents would you select and why? Does the solution contain calcium ion, yes or no? So you're going to take some of this reagent, a few drops, and add it to the test solution. Which one are you going to pick? I got a vote here for sodium sulfate solution. How many also want to vote for the sodium sulfate solution? How many want to vote for sodium hydroxide solution? How many want to vote for sodium carbonate solution? The answer to the question depends on 2 things. What are the 2 things upon which the answer to this question depends? Salt solubility. Which material is most stable in water? Is it calcium sulfate, dihydrate, gypsum, calcium hydroxide, or calcium carbonate? Which of these 3 materials has the lowest solubility in water? Calcium carbonate. You ought to know that from your work in 46L. However, the reliability of this test depends also on an additional solution property. What is this property to which I refer? You're damn right. pH. Because if you've got a solution that's acidic, hydroxide ion is readily murdered. So is carbonate ion. But how about sulfate ion? You murder sulfate ion in an acidic system? Well, the answer is yes, if the system is sufficiently acidic. But do you recall the method that you used to form calcium sulfate dihydrate in 46 laboratory? Do you recall the reagent mix that you made to produce calcium sulfate? Anybody remember? Well, you use calcium chloride solution to supply the calcium ion. What solution did you use to supply the sulfate ion? Anybody remember? If you followed directions in the lab manual, you used 3 molar sulfuric acid solution. How about that? How do I know this? I wrote the damn lab manual. What does that tell you about the solubility of calcium sulfate in a solution that's particularly acidic? Particularly soluble? If you can make calcium sulfate by mixing sulfuric acid solution with calcium ion. Is sulfuric acid solution 3 molar pretty acidic? You're damn right. Yet calcium sulfate will form in this system. Calcium sulfate particularly soluble in high concentration of hydronium ion? Doesn't seem to be, does it? How about calcium hydroxide? You going to make calcium hydroxide in any kind of appreciable molarity of hydronium ion? You going to make calcium carbonate in any kind of appreciable molarity of hydronium ion? No and no. So your choice of reagents is twofold. All things being equal, you take the carbonate solution. Because calcium carbonate is the most stable, least soluble of these 3 materials in water solution. But you also have to consider solution pH. More on that in a minute when we do question 1912. Now then, what calculations can we do to verify what I have just stated? Here's KSP for calcium sulfate. The sulfate ion molarity we shall imagine to be fixed at 10th molar. So instead of adding the sodium sulfate solution to the calcium ion containing solution, let's imagine we're adding a few drops of the calcium ion containing solution, or the solution which may contain calcium ion, to 10th molar sodium sulfate, so we can make the statement that the sulfate ion molarity is in essence fixed at 10th molar. Because if I add a few drops of the calcium ion test solution to the sodium sulfate solution, then I'm not going to dilute the sulfate ion to any extent that matters. Well, here's the arithmetic. If I calculate the calcium ion molarity for this system, I get this. It's just this, the KSP divided by this, the sulfate ion molarity. Now what does this number mean? It means if my calcium ion test solution does have calcium ion in it at a molarity above 9.1 times 10 to the minus 5, Q will be larger than K. Remember Q from chapter 17? And calcium sulfate will have the opportunity to form. Precipitate, if you prefer that word. For the calcium hydroxide solution, what is the trip over calcium ion molarity if I'm trying to precipitate calcium hydroxide with 10th molar sodium hydroxide solution? Well, it's this KSP divided by 0.10 quantity squared. What is this divided by 0.10 quantity squared? I don't want to say any push buttons. 3.0 times 10 to the minus 3. Well, I'm telling you what, this is a much more sensitive test for calcium ion than this, the sulfate precipitation, because the sulfate at 10th molar can find calcium ion at a molarity above 9.1 times 10 to the minus 5. But if I'm going to get calcium hydroxide to form with 10th molar hydroxide ion, that calcium ion has got to be greater, have a greater concentration than 3.0 times 10 to the minus 3. This is a lot bigger molarity than that. That means the sulfate precipitation test is much more sensitive. It can find calcium ion at a much lower concentration than can hydroxide ion. But if I do the same arithmetic with calcium carbonate, and the carbonate ion molarity is fixed at 0.10, then I will get calcium ion to form at a molarity of calcium ion that's above 6.2 times 10 to the minus 8. Now comes another question. You're in the laboratory. You see this bottle. That is to say, that's the label you see on the bottle. What does that label mean? It means in preparing this solution, per liter volume of solution, the stock folks have dissolved 0.10 moles of sodium carbonate. That's all it means. So now when you're in the laboratory and you see this bottle bearing the label 0.10 molar sodium carbonate, do you believe the molarity of carbonate ion in that solution is 0.10 molar? Do you believe that? Do you believe the true molarity of carbonate ion in that solution is bigger or smaller than 0.10 molar? Why? Because carbonate ion, when you dissolve it in water, does what? Hydrolyzes, doesn't it? And it converts to a significant extent to hydroxide ion and bicarb ion. How about that? So if you do the arithmetic, you'll find out in a bottle labeled 0.10 molar sodium carbonate solution that the actual carbonate ion molarity, if my memory is right, is about 0.090. But that's still a rather substantial carbonate ion molarity. And with that solution, the bottle that's labeled 0.10 molar sodium carbonate, with all other things being equal, you will much more readily precipitate calcium ion. Because calcium carbonate is much less soluble in water than calcium sulfate or hydroxide. All right? Now then, let's go to question 1912. Let's imagine we have a water solution which is observed to have a pH of 6.00. We want to test this solution for calcium ion. Should I add sulfate ion and give calcium ion the opportunity to precipitate as gypsum, or should I add carbonate ion and give calcium ion the opportunity to precipitate as calcium carbonate? What should I do? Well, let's do some arithmetic. You, I hope, remember carbonate ion to be present in solution at a fairly high molarity? Yes or no? Hell no! Carbonate ion is too strong a base to live at this kind of pH. In a system at pH 6, you will, practically speaking, find zilch carbonate ion. But what about sulfate ion? Is the presence of sulfate ion affected much at all by having this mildly acidic solution with a pH of 6.00? What will you do to find out? How will you get at the hydrolysis extent of sulfate ion at this pH? Well, let's look at the hydrolysis equilibrium reaction. There it is. So sulfate ion is a weak base, so on hydrolysis, sulfate ion will make the conjugate acid of sulfate ion and hydroxide ion. For this, K is Kb sulfate ion. I'll dial this up from my memory banks and get this alarmingly huge Kb value of 8.3 times 10 to the minus 13. Do you accept this statement, alarmingly huge? I'll tell you a story. I like stories. Much of what I have learned about teaching came from my experiences here as a first-year graduate student starting in 1967. Working with Professor John Franklin Baxter, who was a renowned lecturer of general chemistry. Back in those days, there was a television program broadcast nationally and sponsored by Encyclopedia Britannica called Continental Classroom. He was the guy who gave the lectures for chemistry for Continental Classroom. He liked to see if students were in fact paying attention during lecture. And he often did lecture, which parallel laboratory work, which I try to do also. To me, the fact that laboratory is separated from this course as a 1-hour credit registration is immaterial and irrelevant. Chemistry lecture and chemistry laboratory must be married academic adventures for your learning of chemistry to be sound and meaningful. Has to be. Now, I don't know what the other lecturers do regarding laboratory. I can't control that. But I do everything I can to make lecture and laboratory blend together. Because this is a laboratory science. It's all founded on experiment. So I want what we do in this class to be founded as much as possible on what you're doing in laboratory. Well, in any case, one day Professor Baxter was doing an investigation with common household vinegar, to which chemists would identify as what? Acetic acid solution. You did some work with acetic acid solution, didn't you? Simple titration experiment in Simon 345 laboratory. Okay. And while staring intently at the class, he took a beaker of open vinegar and went like this, very gently wafting the atmosphere above the beaker toward his nose so he could make a careful sniff test. And he said, "Smells just like ammonia." And he went on his way. The next day in laboratory, because I was in that lecture. And now the next day in laboratory, because I also taught the laboratory, there was a student. And he had written in the laboratory manual, where the laboratory manual invited him to make a sniff test of vinegar solution and describe the nature of the aroma. And he wrote in there, "Smells just like ammonia." And I looked at that, and I got a smile on my face. I said, "Do you really believe that?" And he said, "Hell no, but you can't argue with Baxter." It's funny. You got to be careful. Students walk away from here thinking everything I say is some kind of gospel. Don't you ever do that. A very, very important feature of somebody who's going to be good in science class is that you must be a skeptic. You doubt everything. You doubt it critically. That doesn't mean you deny it or disbelieve it, but you doubt it. Until in your mind, what has been said makes sense and you accept it as being reasonable. Don't accept it. Don't. Always question, especially in science class, all the time. And don't tell me that vinegar smells like ammonia. All right? So on we go with this. And we write, the chemical version of Kb for sulfate ion. And just as we did when we played with the bicarb carbonate equilibria and the bicarb H2CO3 equilibria the other day, I'm going to take this and rearrange it. Sulfate ion is going here. Hydrogen sulfate ion is going here. Because what I want to do is at a pH of 6 is to get a concentration ratio between sulfate ion and hydrogen sulfate ion. So I'm going to get this. Here's the hydroxide ion molarity at pH 6. And when I write this, I won't even bother with these. Look at this ratio of exponents. So from a gee whiz standpoint, I have just shown that at a pH of 6, the sulfate ion molarity is 10,000 times bigger It's even about 12,000 times you do the arithmetic. But the ratio of exponents tells us the sulfate ion molarity is more than 10,000 times bigger than the hydrogen sulfate ion molarity. So, at pH 6, does sulfate ion change its nature by hydrolysis? Hell no. So, at pH 6, how may I calculate the solubility of calcium sulfate? What do I do to get the solubility of calcium sulfate correctly calculated at pH 6? What do I do? I take the square root of KSP, right? Because what I've just shown is the acid-base part of this puzzle doesn't mean anything. Fair enough? So I'm taking the square root of 9.1 times 10 to the minus 6, which gives me a value of 3.0 times 10 to the minus 3. So at pH 6, we'll write this down. S solubility equals 3.0 times 10 to the minus 3. Enough with that. Now then, how about S calcium carbonate? Do you remember the equilibrium considerations which we have to make to get at this? Because we've already looked at S calcium carbonate in a system buffered at pH 8. Remember that? So I'm going to go G right away to this quickly and say, remember, S equals calcium ion molarity equals this. The solution is mildly acidic. Right off the bat, which of these carbonate containing concentrations can I X out? Carbonate. Hell, this doesn't exist hardly at all at pH 8. At pH 6, forget it. Now then, if I want the S value, I'll go back to this equilibrium. Doesn't have to be the equilibrium that I use, but this one will work fine. Because this equilibrium shows chemistry of carbonate ion as a consequence of hydrolysis. And we found that K is 1.3 times 10 to the minus 12 for this thing. That's calcium ion molarity times bicarb molarity times 1.0 times 10 to the minus 8. Because that's hydroxide ion molarity at pH 6. Okay? So just as we did before, when we looked at determining the calcium carbonate solubility at pH 8, calcium ion molarity is S, and this we'll put as question mark, because in order to solve this puzzle, we need to find out how the bicarb molarity relates to S at pH 6. Which equilibrium do we need to get at this? Ka bicarb or Kb bicarb? Which one? Kb, you betcha. Because the Kb bicarb equilibrium will give us a handle on the relative concentrations of bicarb ion and hydrated CO2. That's what we want, because we already recognized, forget carbonate ion. So I'll write down, reconsider, abbreviation, RECONS period, Kb bicarb, 2.4 times 10 to the minus 8, hydrated CO2, times hydroxide ion molarity over equilibrium molarity bicarb ion. And then what I did before, or I shouldn't say that, what I did before was to put this over here and this over here and put this under hydroxide ion. I'm not going to do that this time. Because this time I'll take advantage of what we recognized when we paid attention to this previously, in that at pH 6, which molarity is larger? This or this? Which of these molarities is larger? This is 1 times 10 to minus 8. So I'll put 1 times 10 to minus 8 over here. And I see that the ratio of this molarity to this molarity is 2.4 to 1. I mean, I don't know about you folks, but when I do ratios, I want something to 1. To me, that's the easiest way to do it. If I invert this, I can also get something to 1, but I'd rather have the larger number on top. It's just the way I like to deal with the numbers. Either way is okay. Do you recall, if you invert this, you'll get 0.42 to 1? Well, I'm going to keep it this way, 2.4 to 1. So what have we found out? That at pH 6, this mole concentration ratio exists between hydrated CO2 and bicarb ion. Okay so far? I haven't done anything fancy. So, I am now in position to see how the bicarb molarity relates to S. How does it relate to S? How many bicarb molarities is equal to S? You see this? What is this in terms of bicarb? So S is 3.4 bicarb molarities. Nothing fancy about this. So bicarb molarity is S divided by 3.4. All done. Now I know that a number of you folks will, in this case, in the proverbial fashion, not see the forest for the trees. Because you're mystified by these chemical concentration terms. So you're driven to say, let's call this X and Y and all that junk. Don't do that! Sure, this will take up a little bit more of your ink or your graphite. So what? Because if you use the actual chemical formulas instead of X's and Y's, you won't lose sight of what you're doing. Well, I'm in position to solve. I got now a K expression which contains but one unknown, that's S. So I'll do the arithmetic and I get S equals, I think it's 2.0 times 10 to minus 2. I don't know, let me look. Where the hell is it? Mm-hmm. 2.1 times 10 to minus 2. So, at pH 6, which stuff is easier to form? Calcium carbonate or gypsum? Which one? There's the gypsum solubility. Is this a smaller number than this? You bet it is. That means the gypsum is easier to form. Now, let's put on our thinking caps and imagine we're in the laboratory. You are now dealing with an unknown for Simon 5. This sample may or may not contain calcium ion, because calcium ion is part and parcel of your Simon 3 investigations. The solution is laced with sodium ion. Flame test tells you this. Your gee-whiz indicator analysis tells you the solution has a pH of 6. You want to find out if it's got calcium ion in it. Flame test positive, gee whiz pH solution 6. You go to the laboratory side shelf, you're sticking out your hand. Do you grab the sodium carbonate solution or the sodium sulfate solution as your precipitating agent? Which one? I'm taking sodium carbonate solution. Because that solution you have in the laboratory is or is not a buffer? Is or is not? Is or is not? Is not, damn it. So as soon as you start putting the carbonate in there, the pH is going to go bee. And when the pH goes bee, calcium carbonate's a lot easier to form. Don't ever forget thinking about what the hell's going on. Pick it up from this point next time.